Hi there, it's Paul Bamberg back with another Math156 script. This one is on confidence intervals, a topic that's treated very, very nicely in Chapter 7 of the textbook, but that unfortunately is used in Chapter 5. So I thought it would be useful for you just to have a brief introduction to this rather tricky topic. Let's consider the simplest case. We're sampling from a normal distribution, and we know everything. We know it's normal. We know that it has a certain expectation, a certain variance, and we also know the sampling distribution for the normal distribution. It's another normal distribution. To be specific, let's suppose that we take a normal distribution with a mean of 23 and a standard deviation of 7 and draw samples of 50. Recall that when you take the sample mean, you divide the variance by the sample size. So the variance for the sample will be 7 squared over 50. Now, if we take the sample mean, we've got a 50% chance of getting something that's less than the expectation 23, a 50% chance of getting something that's greater. And what we'd like to do is come up with a number that's got a pretty high probability of being greater than the true sample mean. In other words, we want to guard against the possibility that we accidentally got a sample with a rather low mean, and we're going to add on a quantity. I'll call it x sub add, so that when I take x sub bar, the sample mean, and add on x sub add, the result, let's call that x dot top, will be greater than the true mean 97.5% of the time. In order to do that, I have to be sure that the probability that the sample mean is less than mu, the true mean, minus the quantity I added on, is going to be 0.25 or less. And this gives me the standard formula for the upper endpoint of the confidence interval. Check the math notes for a more detailed treatment of this. The funny thing about it is, to x dot bar, the sample mean, I add mu minus q1, where q1 is the lower quantile. At first it strikes people as strange that you should add on the lower quantile, but then you think about it, what are you trying to guard against? You're trying to guard against the probability that you got a sample that is much, much smaller than the expectation, and therefore you want to add on something that is the difference between the true parameter, the expectation, and the 0.025 quantile, the value below which you will go only 2.5% of the time. So now let's start doing this. Here is x dot add. We take the true parameter, which we happen to know, and we subtract off the 0.025 quantile for a distribution that's normal with an expectation of 23 and a standard deviation that's 7 divided by the square root of 50. Now, 1,000 times, let's make a plot where we draw our random sample of 50, compute the mean, and add on this quantity x dot add that we carefully calculated from our knowledge of the theory of the normal distribution, and we expect that most of the time u will be large enough that it's greater than the true mean. If that's true, if u is greater than the actual expectation of 23, we will add 1 to our counter. And for the first 100 tries, which is all we can plot, we will plot the value of u. So now we've done that. Reading from top to bottom, you can see the values of u for our first, second, third, and so on experiment. There is a vertical line drawn at the true mean, and it looks as though we're doing fairly well. Almost all the time, the quantity u that we calculated is greater than the true mean. In fact, I see only one example where it's smaller, but we have the full 1,000 to look at. If we take counter divided by 1,000, we see that 978 times out of 1,000 we computed a quantity u that was greater than the true mean. We were shooting through for 0.975, so we came out fairly close. And we can do the same thing on the low end. We have to subtract a quantity. I'll call it x dot sub, and this is to guard against the possibility that our sample mean came out extraordinarily high. We're going to subtract off something that will drag it down to a level that's most of the time less than the true mean. Okay, there's our computation of x dot sub. I can compute that, by the way, only because I know everything about the population from which I'm drawing these samples. And we'll do exactly the same result. Set up an empty plot. Draw our sample 1,000 times, subtract something to get the lower end of the confidence interval, add 1 to our counter if we successfully get something that is less than the true parameter of 23, plot the results for the first 100 trials, put a line at the true mean, and you can see most of the time we came out just fine. In fact, it almost looks to me as though we really lucked out, and 100% of the time we computed a number that's less than the true mean. But if we look at all 1,000, we see 976 times we succeeded. That's what we were shooting for. Now, here's the tricky thing about confidence intervals. The value 23 is not a random variable. It's a parameter of our distribution. The random variables are the quantities L and U that we computed. We computed those by drawing a sample, taking the mean, and then adding or subtracting an appropriate amount. So the confidence interval that we talk about is specified by 2 random variables, and our goal is that the random variable L most of the time should be less than the true expectation for the distribution, that the random variable U should be higher. And now I can show the whole confidence interval on a plot. I make a blank plot. 1,000 times I will draw a random sample. This time I will compute both L and U. I will score 1 on my counter if I picked an L that's less than 23 and a U that's greater than 23. And for the first 100 tries, I will actually plot a horizontal line that runs from L to U. That's what the segments function in R does for me. And here's my plot. Here's how to interpret it. 100 times I calculated a confidence interval which is represented by that black horizontal line. Its endpoints are random variables. They vary from one trial to another. There is the true value of the parameter, and you'll see most of the time that true value lies within the interval, but on occasion, here's an example, the entire interval will lie below it. On other occasions, here's a very clear example, the full interval from L to U will lie above it. Our goal was to get the true value 23 lying within the confidence interval 95% of the time. How did we do? Pretty well. 953 times out of 1,000 we picked a confidence interval that included the true value of the parameter. Okay. Now let's change this very slightly. Let's use a skewed distribution. We'll use a gamma distribution with a shape parameter of 1 and a rate parameter of 1/2, and the sampling distribution is therefore something with a shape parameter of 16 and a rate parameter of 8. So again, we know the actual sampling distribution, but it's not a normal distribution. It's a skewed distribution, and theory says it's got a mean of 2 and a variance of 0.5. There's the density function. You can see it's definitely skewed to the right. And using Q gamma to get quantiles, I can plot a couple of vertical lines so that the random variable is going to be less than the value shown by the left-hand red line 2.5% of the time, greater than the value showed by the right red line 2.5% of the time. Now, if all we knew about this sampling distribution was that it had a mean of 2 and a variance 1/4, we'd probably have to gamble on the central limit theorem and use a normal distribution. And this is what lots of folks do. In computing confidence intervals, they say, I don't know anything else. I'll assume a normal distribution. Maybe I'll luck out. But in this case, we can certainly do better because we know the actual sampling distribution. So here's what we would get if we use the quantiles for the normal distribution. Notice those differ significantly from the actual quantiles from this distribution. And if you base a confidence interval on the assumption that the distribution's normal, that discrepancy between the red and blue lines is going to show up as an error in your confidence interval. So let's compute the correct quantity to add. The correct quantity to add is based on the 0.025 quantile of the gamma distribution. It uses the lower quantile. We're trying to add on a number that's large enough to guard against the probability that we've accidentally generated a sample that's too small. And we are therefore adding on a lot in an attempt to get a number that most of the time will exceed the true value of the parameter. We can do the same with x sub, and we can generate some confidence intervals. We make a blank plot 1,000 times. We generate our sample of 16 from the gamma distribution. Subtract off this x dot sub to get the lower end. Add on x dot add to get the upper end. And if we actually compute something that is less than the true value of the parameter 2, we score 1 in the low counter. If we generate a u that's greater than 2, we score 1 in the high counter. And 100 times we make one of these lovely plots, which I had never seen before I encountered them in the textbook, where we plot the confidence interval as a line segment. So there are our confidence intervals. There is the true mean. And you can see we've done pretty well. Most of the time, but not quite all the time, we generated a confidence interval that included the true mean, but on occasion we missed. And if we take the low counter and the high counter and divide by 1,000, we see we came out fairly close to our target. Roughly 97% of the time, both ends were correct. If we use the central limit theorem approximation, saying we use only our knowledge of the expectation and variance, what would happen would be that we'd miss more on one side than on the other. If I compute x dot add from the quantiles for the normal distribution with the correct expectation and variance, and do the same for x sub, we can generate some confidence intervals. I'm doing exactly the same thing, generating from the gamma distribution, but then adding on quantities that would correct appropriately for the normal distribution with the same expectation and variance. And when we look at our plot, we see, well, indeed, 95% of the time, that red line does intersect the confidence interval. But when we look at the low counter and the high counter, we see that we missed many more times on the low end than on the high end. And that's the problem with blindly assuming a normal distribution for a confidence interval. With a confidence interval, not only do you want to try to make the probability that the true value of the parameter lies in the confidence interval 95%, you would also like to miss 2.5% on the low end and 2.5% on the right end. So now you can ask, what are we going to do if the sample is too small for the central limit theorem to be trusted? And furthermore, we don't know the sampling distribution for the population. The answer to that question which will be addressed in the next script, is we use a bootstrap estimate of the sampling distribution using the actual data to try to reconstruct a plausible sampling distribution.